Hi 253. In this video we are going to talk about section 10.3, Calculus in Polar. So we already talked a little bit about this section together in class. We talked about how we can take derivatives when we're working in polar, but now let's think about the other major technique from calculus, thinking about integration when we're working in the polar coordinate system. So the question is, how can we find the area under a polar curve? And I had to put this little sort of quotes here about being under a polar curve, since as we know, working in the polar coordinate system means we're not in a rectangular system, so under is kind of a relative term since our curves here have some sort of, they're produced in like a rotational way, right, as theta varies. So the issue is, we're not going to be able to use our current techniques that we have for our notions of the definite integral, since we're not working in the rectangular coordinate system. So it's not going to be where we're just going to be able to directly say take a definite integral of the function from start to finish, right? We're going to have to do a little bit of reasoning as to how we get perhaps an integral to use. Maybe we'll get an integral. Let's hope we get an integral, right? Since we're still working in calculus. So let's see what we should do. So the idea is that we want to find the area of the region R bounded by a polar curve between the rays theta equals alpha and theta equals beta. So the idea here is that you have some kind of polar curve, right? R equals f of theta. Okay, it's going to do much more than just this little red segment, right? But we're just concerning ourselves with this little piece here because we want to know what is the area bounded by this curve as theta varies between alpha. So that means that this angle here is angle alpha, right? Let me do my little pen for you, right? That means this right here, this is angle alpha, and that means this is angle beta. Okay, so as theta varies from alpha to beta, basically as the angle goes from here to here, what is the area that is enclosed by this polar curve as that angle theta varies? So notice that since I'm saying as the angle theta varies, as theta changes, those kinds of things, that means really we're thinking about here theta as being our independent variable, right? Just like when we integrated in the rectangular coordinate system, when we accumulated area as x varied, right? That means we were calculating area underneath a function, and we said we needed to integrate with respect to x in that case. Well, now, since theta is the variable that is varying, right? Okay, and we're accumulating area as it varies. That means we're going to need to integrate with respect to the variable that is varying, or theta, right? We're going to need to integrate with respect to theta. All right, so as you can tell, this might be a little bit of a tricky process because with rectangular coordinate system, we just talked about constructing a Riemann sum, taking a limit, and we used rectangles with that whole process, but as you can see, rectangles are probably not going to be the best way to go about this because, again, the curves are produced in a rotational sense, right? Not in a rectangular coordinate system. So we're going to have to get a little bit creative here. So the idea is that we can actually take from the rectangular coordinate system is this idea of approximation. We're going to use the same concept from the definite integral in rectangular coordinates. We're going to take small slices of the region R, and that's going to allow us to approximate the area. But the slices that we're going to be thinking of are not going to be rectangles. These slices that we're going to be thinking about, they're going to be approximated by area of sectors of circles, right? So the next slide will sort of give you a little bit of a better idea how this is going to work. But just for a second, let's recall how we actually find the area of a sector. So a sector, remember, is just a portion of a circle drawn out by some angle theta here, right? So the area of a sector, remember, this is a formula we just can take for granted. Maybe you proved it somewhere else, or you can just remember it, right? This is area of a sector is 1/2 r squared theta, where r is the radius of the circle, theta is the angle creating the sector. Okay? So let's see how this can actually be useful for us when we are trying to work here in our polar curve. Okay, let's see if we can get a nice picture. Okay, that's really scary, right? Let me walk you through what this scariness is actually doing here. So notice that we still have our area, our region here R, right? Our region R is what the region bounded by this polar curve as theta goes from angle alpha to angle beta. Okay, so really the area, the region R that we're trying to approximate here, get the area of, is that big region right there. Okay, so the idea is we're still trying to figure out what the area of R is. What we're going to do is we're going to divide R into wedge-shaped slices, right? So the idea is sort of put all of these like rays like this, right? Slice it up kind of like a pizza, right? The only problem is that our pizza has kind of a lumpy crust, okay? That's the problem. If it was a perfectly round pizza, we wouldn't have a problem because we know a formula for the area of a circle. The problem is, again, just like from Calc 2, right? The edge of our polar curve here is not uniform, right? It's not anything nice, like it's not a line, it's not a nice arc like a curve of a circle or anything like that. It's not uniform, right? It does weird stuff. Okay, so we have to approximate. So what we're going to do is make these wedges. Each one of these little wedges is going to be able to be approximated by a sector of a circle, right? And this is where we actually get the approximation. So notice here, just like before with those rectangles, where we had a little bit over, a little bit under, that kind of an approximation, we're doing the same thing here. So each one of these little wedges is going to be able to be approximated by the area of a sector. And that's actually what we have here, is each one of these pieces is actually the area of a sector. Now it's part of a much bigger circle. For example, this one up here, right, this sector right here that we're working with, this one would be one little tiny slice of a much bigger circle, right? Okay, so the rest of this circle would be something that looks like this, okay? But again, we're just taking one little slice of it. We don't need to think about the rest of the circle because we know how to find the area of just a sector of a circle, and that's all we're worried about, is finding the area of this little pizza slice here, right? Okay, and we can do that for each one of these wedges. We can approximate it with one of these pizza slices, one of these slices right here, right? Which are sectors of circles specifically. The reason that we can do that is because here, notice we're taking this sort of non-uniform piece of a polar curve, right, in that little slice right there, and we're using now a nice uniform piece or edge of a circle, right, so that we have the formula for area of a sector of a circle to use. Okay, so once we've done this, we've divided it up into, it looks like, how many pieces? Can you tell? Notice the subscript here on theta sub n. Just like with rectangles, that means that we've divided this into n little pieces, right? So we've divided it into n wedges, okay? So since each of these is the sector of a circle, we can find the area of each one of these pieces individually. That would be a very long, tedious process, right? But let's just talk about one of the slices in general, one of the little sectors. So we'll pick out the kth slice. Of course, you can probably see where this is going, right? The kth slice is going to be, is approximately, right? So this, the actual wedge of R itself is approximated by the sector of this circle that we have here, right? This sector of a circle approximates the wedge of R, okay? Fairly well, I would say. There's a little bit missing here, but a little bit extra there. That's okay. So this kth slice is approximately a sector of a circle, and what is the angle? So now just don't get lost in the notation here, right? This delta theta sub k just means you are in the kth interval, right? The kth wedge here, and delta theta sub k just means that the angle generating this sector right here, this little part of a circle here, is a change in an angle, right? So that's the angle change to go from an angle of theta sub k minus 1 to theta sub k. That's the change in the angle, okay? And remember, that's actually what we need to write the area of a sector, right? Remember, we need to have what the actual angle measurement is, right, to calculate the area of a sector, okay? So that means that we have, let's see, an angle theta sub delta theta sub k, and the radius of that circle would be what? Now that is making use of that point right there. Yes? Okay? And that's where we get the theta sub k bar, right? We have this bar right up there because we're just saying that that point right there is somewhere between what would be theta sub k minus 1 and theta sub k. Okay, and maybe this picture over here helps a little bit better once we removed all the other parts. Okay, this is the little wedge I was just talking about, the little sector, right, approximating the wedge of R. Okay, that's the point f of theta bar sub k, comma, theta bar sub k, right? Okay, because we're in polar, remember it's r sub r comma theta, that's the ordered pair. And so here, since we have, that's the radius, that f of theta bar sub k, got to be careful about how we say it, okay, that's r, and then the angle that creates that sector is delta theta sub k. So how do I find the area of that sector right there? Remember, that will be this formula, 1/2, I take the radius and I square it, and then I multiply by the angle, right? So again, it's making use of this 1/2 r squared theta idea for area of a sector of a circle, right? There's the 1/2. The radius is what? This right here. This is the radius, and the angle measure that creates that sector is delta theta sub k. Okay? So that's just for the kth slice, and notice that the area of the kth slice, the wedge is approximately that, right? Because we're approximating. Okay, well, what do we do with that? If we know the kth slice, what do we have to do to approximate the entire area of R? We have to add up all the slices, right? And how do we add up a bunch of things? You're guessing it correctly. We make use of a sum, right? So the area bounded by the polar curve from angle alpha to angle beta is approximately, notice the approximation, right? Because we're approximating by using sectors of circles. So this is the sum from k equals 1 to n because we used n wedges. And here is what? This is the area of each of the sectors, right? Isn't that the case where we just had that on the previous slide, right? 1/2 r squared theta, right? 1/2 r squared theta, right? So we're just adding up the area of all the wedges, or of all the sectors, right? Area of all the sectors, adding all of them up. Now, well, we don't want to just be happy with a little squiggle approximation. We want equality. We want true equality, right? And when does that happen? Under a limiting process. So when we apply a limit, what do we get? Let n go to infinity for this sum, and we poof, magically, there's more than just poof magic happening here, right? There's a lot of not tricky, but sophisticated calculus that goes into proving this, right? So what we end up getting is the following integral. We get the integral from alpha to beta as theta varies, right? And the integrand is 1/2 f of theta squared, right? So you square the function that you are, the polar curve that you have, I'm sorry. You square the polar curve you have, multiply by 1/2, integrate from alpha to beta, and you're done. So how about we try an example? This is the formula we're going to be making use of. So let's find the area of the region inside the circle r equals 8 sine theta. So hopefully, before you started watching this video, you did the week 4B workshop that I handed out in class, which was the practice in matching Cartesian and polar graphs. So that you're kind of getting an idea of what this graph looks like. If you haven't done that activity yet, pause the video right now and go do that activity, and the answers are posted to Moodle so that you can check your work to make sure that you're matching them correctly, so that when I show you the graph of this thing, you're not surprised. Okay, so let me just now show you what it is. Hopefully you've paused the video and come back, right? So let me show you what the graph of this thing looks like. I'm going to make use of the polar grapher that I also uploaded to Moodle for you. This is the polar function grapher. Again, on your Moodle page, I put a link at the top of our Moodle site for this for you. So here I've plugged in the function r equals 8 sine. Now they want you to use a t instead of a theta. That's because it's easier to write a t. I'm going to go from 0 to pi. The reason you'll see that in just a second is because over that interval 0 to pi, sine of theta would go from 0 to 1 to 0, which is going to completely generate the circle, as you'll see right now. So here's my little interval for theta. I start at 0, and now the curve is being drawn out in green. The line that you see is the value of theta that is producing that point, right? And this is in radians, again, not in degrees, right? It's important we're working in radians when we're doing polar graphing. Okay, so now notice here at pi over 2, right? That was where I actually reached the top of the circle because that's when sine would be 1, and again multiply it by 8 because we have an 8 in front. That's how you get the height of our circle here. And now we see it coming back down because sine is now approaching being 0 again when we reach pi. Okay, so the entire circle has been mapped out from 0 to pi. And so I'd like to find the area enclosed by that circle. Now I know you're probably telling me there's a lot easier way to do this than to use a integration when we're in polar. It's just a circle, right? But this is just for practice, right? Okay, so let's actually get back to our slideshow here. It won't let me do that, so I'm going to have to go. There we go. Okay, so let's go ahead and find the area of the region inside the circle. So notice, remember, we need to be on the interval 0 to pi, right? So if we're going to go 0 to pi, That means that our integral, our area here, that we're going to be calculating is going to be given by this integral, 0 to pi. What was our formula? Do you remember our formula? It is angle alpha to angle beta, so 0 to pi, 1 half f of theta squared d theta. Okay, so remember that this is f of theta, right? This is how we define polar curves, right? So that means that I do 1 half f of theta squared, so this is f of theta squared d theta. Okay, so now let's just see if we can simplify this out. So first of all, this squaring needs to apply to both pieces in here, right? So that would be a 64, but I need to 1 half it, so that's a 32. Integral 0 to pi sine squared theta d theta. Well, look at that. Isn't it a good thing that we talked about how to integrate trig functions before? Trig integrals, right? This is a trig integral, and we can make use of a half angle formula to drop the power on the sine down by rewriting it as 1 minus cosine 2 theta over 2 d theta. The over 2 part can come out and interact with the 32 to leave me 16 integral 0 to pi 1 minus cosine 2 theta d theta. And I think we can integrate this, right? 16 times, now remember we're integrating with respect to theta, so the antiderivative of 1 is theta, minus antiderivative of cosine is sine 2 theta, but we have this 2 over 2 like that. Remember that would have been a u substitution. If you remember how that works, it generates a factor of 1 half in the u substitution, and I need to integrate from 0 to pi. Okay, so now let's just plug in our limits of integration. So 16 times pi minus sine 2 pi all over 2. That's when I plug in pi, minus, let's see, what do I get? 0 minus sine of 0 over 2. Now some of that was redundant. I didn't need to write it because you'll see that lots of these pieces go to 0, but I wrote it just so you can see. What's nice is that goes to 0, this is 0, and that is 0 also, right? So what that means is the area enclosed is 16 pi. And I'm guessing that the area of the circle would have been 16 pi if we didn't use a definite integral either, right? Yes, it would have been, because the radius of that circle was 4, right? So pi r squared. Okay, excellent. So now the next question becomes, just like it was in Calc 2, right? What if we wanted to find the area between two polar curves? Meaning, what if I have this like sandwiching problem here where I want to say, well, not just the area of the stuff under the graph of f, but what about the area of the stuff under f but above g, sort of sandwiched between the two? Okay, well, let's, just like we did in Calc 2, we can kind of reason through what would happen here. I know there's a formula down here, but let's see why it works, right? So notice that the area under f, and I'll be careful here and say it like this, right? Right, that would be given by what? I would go from alpha to beta, and I would have 1 half f of theta squared d theta, right? Well, what would then, so that would be everything, right? All of that stuff, right? That would be everything underneath all of that, right? Well, if I just want the blue stuff, then what do I have to do? I have to take everything that I just kind of outlined right there, and I have to subtract away this stuff. Yes? If I take the big outer part and subtract away this little part here, that's going to leave me with this area right here. Yeah? Well, can I write this area here as something? Yes, that's the area under r equals g of theta, right? And that would equal what? This should be dots, not equals, by the way, just for cleanliness, right? So this would be what? This would be integral alpha to beta 1 half g of theta squared d theta. Okay, so if I just want to subtract that away or take that away, I'm going to subtract, right? So the area under f but above g, this stuff right here, that's going to be this first one here minus this one here. But because of our properties of integrals, the integral can then just be written as a single integral. The difference of the two integrals can be written as a single integral. Here we have 1 half, and then we have f of theta squared minus g of theta squared, right? And if you want to write the 1 half out front, that's fine, right? So you could write this as 1 half integral alpha to beta f of theta squared minus g of theta squared d theta. All right, let's give it a try and see if we can do it. All right, so let's find the area of the region inside the lemniscate r squared equals 2 sine 2 theta. Remember, that's a crazy word, right? You can either say lemniscate or lemniscate, right? One of those two is either one of those two is fine. Or just try butchering it, it'll be fine. So here's we want the region inside of the lemniscate, or lemniscate, r squared equals 2 sine 2 theta, which I have sketched here. Thank you, Wolfram Alpha. And outside the circle r equals 1. So I've just drawn the lemniscate here. Again, make sure that you practiced your week 4B workshop. That'll help with knowing why this is the graph of this. But if I want the area of the region inside of this but outside of the circle, well, I don't have the circle drawn, but I can easily draw the circle, right? I can just draw it on top. That's going to look something like this. And that wasn't too bad for doing that on a bamboo tablet. So the area inside of the lemniscate and outside of the circle, that's going to be this stuff. Yes? Right? Well, how do I go about finding that area specifically? Well, I can make use of the formulas we just did a second ago. I can also be a little bit sneaky here, right? Because the issue is that I've got a lot of symmetry going on here, and so instead of saying I'm going to try to do both of these areas, if I actually just did one of them and doubled whatever I got there, then I'd be done, right? Okay, so first of all, what we need to do is figure out where these two curves actually intersect, because what I have to know is what is the angle measurement here and what is the angle measurement here producing where these two curves intersect, right? Because remember, that was important back here. I know we didn't have any intersections because we just were given alpha and beta, but here we don't have just given alpha and beta. They just want to say bounded by the lemniscate and the circle, right? So we actually have to find where these intersections occur. Okay, so how do we find intersections? Well, remember, that's when we set two curves equal to each other, right? Well, notice that we have this equation and this equation. If we want to use them simultaneously, that just means we have to replace what? R in this equation with 1. Okay, so just to find the intersection first, so that we know what our angles need to be that we're going to use, I have to do what? 1 squared equals 2 sine 2 theta, which means I'm looking for when sine of 2 theta equals 1/2, right? So in the first quadrant, right here, for between 0 and pi over 2, which is where we're working, right, that means that we're looking for when 2 theta is equal to pi over 6, which would give me what? Theta is equal to pi over 12. Sorry about the equal signs again. The other one I could possibly get would be 2 theta being 5 pi over 6. And that would give me theta is equal to 5 pi over 12, right? Okay, so again, if you don't remember that, if you don't remember that, you might want to sort of review your unit circle a little bit, right? So that you're ready to go with those angles that are producing values of the trig functions here. And again, why is it 2 theta? Because that's what the angle is living inside of the trig function, producing the value of sine. Okay, so now that we've got our angle measures here, that means we can go ahead and write area will equal the area of the whole thing is going to be what? I'm going to have to double whatever I get right now because I'm just doing this piece, but I know that there's by symmetry another part of it over here, so I'm going to double it, right? So that's really saying 2 chunks. Okay, I'm going to go from pi over 12 to 5 pi over 12. And now what do? I do 1/2 times outer function squared minus inner function squared. Outer function squared is this outer lemniscate, right? Okay, so I do f of theta squared. Well, notice here that we have r squared equals this thing, right? We always have defined our equations to be r equals f of theta, right? What that really means is that we're already given the function squared. We're given r squared, right? So that actually is already f of theta squared, right? That is f of theta squared. So it's just 2 sine 2 theta minus inner function squared, 1 squared. Okay, remember this part right here, this is r squared. We already have that part, okay? They gave us that because of the way the lemniscate is defined. That's already r squared.